Okay, we're now on to Trigonometric Identities and Equations, which is pure year 1, chapter 10. And we're going to start off with some more definitions for the tan function and the Pythagorean identity and the cofunction. And then we're going to do some equation solving over here. So for the tan and Pythagorean identity, I want to start off by thinking about a triangle where the hypotenuse is 1 and the angle is theta. Let's just quickly investigate what sine theta would be equal to. Well, having a think about this, sine theta would be equal to the opposite divided by the hypotenuse. So this would be the opposite divided by 1, which just tells me that sine theta is the opposite. So I can now add on to my diagram that this part is sine theta. And I'll do the same thing for cos. I would see that cos theta is the adjacent divided by the hypotenuse. So cos theta is just the adjacent of this particular triangle. Seems weird to label a side length, but the side length is sine theta and the side length here is cos theta. Now, using our definition, we now see that tan theta is the opposite divided by the adjacent. So we can tell that tan theta is the opposite divided by the adjacent, which is sine theta over cos theta. So there is our definition of tan theta that we've got there from the triangle. Now, the Pythagorean identity shouldn't surprise you that it's going to use Pythagoras on this right-angled triangle that we've got here. So I'm going to write down the Pythagorean identity is that sine squared theta plus cos squared theta is equal to 1. And you may use this in some rearranged forms. You may rearrange it so that you have that sine squared theta is 1 minus cos squared theta. And similarly, you may also see it as cos squared theta is equal to 1 minus sine squared theta. But the most important ones I want you to remember are the two that I've underlined, so that tan is sine theta over cos theta, and then this Pythagorean one that we have here. And it comes back in year 2 when we add in some new trigonometric functions. Now, the cofunction identity isn't really explicitly taught, but I think it's worth us exploring that we've got here because it has come up in some exams in the past. So I'm going to begin by investigating what sine theta is on this triangle. Well, sine theta, concentrating on this one, is the opposite divided by the hypotenuse, which is the opposite divided by the hypotenuse. Now, this is actually the same as if we look at this part. I'm looking for b divided by a. It's the same as this angle's adjacent divided by the hypotenuse. So it's the same as the cosine of 90 minus theta. So it's the same as the cosine of 90 minus theta. So the cofunction is that sine theta is equal to cos of 90 minus theta. And similarly, if I worked out what cos theta was from our original triangle, it would be c over a, which is c over a. Hopefully you can tell that c over a is the sine of 90 minus theta. C over a is the opposite over the hypotenuse. So it is the sine of 90 minus theta. Now, the reason this is called the cofunction, where we're saying something like that sine theta is the cos of 90 minus theta, is because 90, this theta and this 90 minus theta, these are called complementary angles. Co for complementary that we have here. Complementary means they add up to 90. And that's actually why sine and cosine, that's why cosine has the co added at the beginning of it, because it is the complementary sign. So if you ever have a 90 minus theta as the angle, you can switch it and say instead of it being a cos, you can change it to a sine. So I don't know, if we had 30 degrees and 60 degrees, we know that they are actually the same as each other because they are complementary. Okay, so a bit of a niche sort of one there. I will be using it later on, but I like to point that out in case it doesn't come up in your lessons. So for solving equations, this is the absolute shortcut of how to solve equations that we've got. So you would have that sine theta, cos theta, and tan theta were equal to something. You would get your solutions. The first solution that you would get from sine theta is just the one on your calculator, which is theta. But to obtain a second solution, you would do 180 minus theta, so that you get these two starting solutions. And then all you need to do for this is you can plus or minus 360 degrees to both of these answers, but you do have to start off with both of them here. Now, even if theta was negative, you would do 180 minus something, it'll be 180 plus something, and that's going to be your shortcut for finding your solutions for sine theta. For cos theta, you get the one from the calculator, and you get 360 minus theta, and then again, you can add or subtract 360 degrees to this one. Tan theta is the easiest one. You just get the theta from the calculator, and then all you need to do to that one is just plus or minus 180 degrees to it. I probably will put these little degree signs on here just to make it look as official as possible. So you don't need to mess around with like graph drawing or cast diagrams. If you can just remember these things here, you will be able to solve all trig equations very, very simply. Now, if you do have an equation with a linear input, what I mean is an input like this. Instead of it just being x or theta, the x part has been changed into something that is linear here, 2x minus 20. What you're going to do is you will change the range first. So you want a range of answers. You would change this range. You solve the equation for the new range, and then you get those answers, and you solve those for x or theta or whatever it is. Now, this is sort of optional. It just makes it a lot easier when you do these questions. So I'm going to probably be using just these bits for these questions, and then this one down here we'll use a little bit more. It's going to use some of this bottom part and probably something from up at the top. And then we'll do a much more challenging one on the second slide that we have. So it says, solve sine x equals 0.6, giving your answers to the nearest degree. So obviously the first thing I will do is the inverse sine of 0.6, which I'm just going to do on my calculator. It's not going to give me an exact answer, but as a nearest degree, it gives me 36.869. So I'm just going to say that it is 37 degrees. And then do you remember for sine, we said the other one that you do is 180 minus theta. So on my calculator, I'll just do 180 minus the answer. And to the nearest degree, it is 143 degrees. Now, I've deliberately not given a range of values here just to kind of explore what we could do. So we've got these kind of like two streams of answers. All you can do now, if you want to, you can add 360 to both of them. So if I add 360 to that bottom one, I get 503 degrees. That's a solution. If I do 37 plus 360, I get 397. If you wanted to, you could take these initial ones and you could take away 360. So minus 323 is also a solution. And then we could do 143 minus 360. Minus 217 is also a solution. So you can do whatever you want to those first two that you get. As long as you're adding or subtracting 360 from other ones that you have, you get these two streams. You'll have these two streams for sine, two streams for cos, but only one sort of stream of answers for tan where you're just adding or subtracting 180. So I deliberately didn't give a range for this one, just to show you that if you did have an unlimited range, you could just keep going and going and going. So for this one, we have the range between minus 180 and 180, and we're going to solve cos theta equals minus 0.3. So on my calculator, I'll do the inverse cos of minus 0.3. We're doing it to one decimal place here. So that is 107. It's 0.45, so that's 107.5 degrees. And then the other solution for cos is 360 minus the answer. I should have jotted down this one here. That was 180 minus the x that we had. So for this one, when I do 360 minus the theta on my calculator, I get 252.5 degrees. Now we've got these two streams. We just need to make sure that they're going to fall inside the range. This one is not inside the range. So what I'll do is I will subtract 360 from this to get it back inside the range. So when I subtract 360, I get minus 107.5 degrees. Now there's not much point in subtracting 360 from 107.5 because if you do, you go beyond the minus 180. And there's no point in sort of subtracting 360 from this because it will go too low. So I'm just going to reject that answer and say that my two answers are 107.5 and minus 107.5 for this. Okay, we're going to do one that's got a different linear input that we have. And I'm going to start off by changing the range that I have like I suggested over here. And I'm going to change the range from 0 to 90. Don't worry about writing the degree signs, you wouldn't get penalized for that. I'm going to try and make it look like this 2x minus 20. So I'll double everything to get the 2x. And then I will subtract 20. So I have 2x minus 20 is less than 160. Now I'm going to try and solve this equation, and when I solve it, I'll try and find answers that are between minus 20 and 160. Now the annoying thing here is we've got a mixture of sine and cos, so I think I'm going to need to employ this thing here. I'm going to need to turn these sines and coses into a tan. And the way I'm going to turn them into a tan is, you can clearly see, you divide by cos theta. So what I'm going to do is I'm going to divide by the cos of 2x minus 20. That will leave me with, when this bit gets divided by cos of 2x minus 20, I will get 5 tan of 2x minus 20. When this thing gets divided by cos of 2x minus 20, you just get left with a plus 2, and that is equal to 0. Now I'm going to make the tan of 2x minus 20 the subject. You'll notice I'm not putting degrees everywhere. It's not really important. When I make it the subject, I will subtract the 2, and I will also divide by the 5. So I've got that tan of 2x minus 20 is equal to minus 2/5 that we've got here. So on my calculator, I'm going to just do the inverse tan of minus 2/5. And what does it want this to? To 1 decimal place. So because I'm going to be doing some equation solving, I might do 2 or 3 decimal places for now, just so I don't lose any accuracy. I'll do probably 3 just to be really extra. So the first one I get on my calculator is minus 21.801. Now I'm going to try and find these solutions for the new range first. Now this minus 21.801 is not inside this range. If I add 20 to it and divide it by 2, it will not be inside that original range, and this is what this one checks for me. So I'm going to just find the next one. We know for tan, we just plus 180. If I plus 180, I get 158.198, blah, blah, blah. Doesn't need to be rounded as long as I've got a few decimal places. So that is inside the range that we've got here. So there's no point in adding an extra 180 onto it because it's going to go outside that range. So I will reject this one. And now I'm going to do the third point, which is just to solve for x. It says solve these for x. I've only got one, so I will solve this for x. So I will say I will add 20 to this, and then I will divide it by 2. So on my calculator, I'm going to press add 20, divide by 2, and then I'll give my answer to 1 decimal place, which I have as 89.1 degrees. And that is to 1 decimal place. Now, if you didn't write these, if you didn't have it stored in your calculator, the reason I wrote 3 decimal places here is because then when I added the 20 and divided by 2, I wasn't losing any accuracy with how I did this. Okay, this is a much more challenging question on this page. It includes an identity, which is with these 3 signs here, that shows this thing is always equal to this thing, and then we have an equation on the second part. So, having a look at the part A that we have, I'm going to see if there's anything I recognize in the numerator. Well, I think the first thing that I want to address is this. In fact, not the 7 part, just the sine of 90 minus theta. I know that 90 minus theta means it's the complementary angle, so I can change it from a sine to a cos. This means that the left-hand side, you don't have to use this triple identity equal sign if you don't want all the identity symbol. I will use it here. The left-hand side is now 10 sine squared theta minus 7 cos theta plus 2 divided by 3 plus 2 cos theta. I'm going to try and make this whole thing 4 minus 5 cos theta. Obviously, it made sense to work on the left-hand side because it was the kind of messier side. It would be very hard to make this thing look like this thing. Okay, I'm going to continue with this. Now it looks like I've got a mixture of cos and sine. I want to get this sine squared and I want it to become a cos squared. So the identity we'll use is the Pythagorean one. We can either use this or we can use this rearranged one that sine squared theta is 1 minus cos squared theta. So I'm going to do 10. We've said that sine squared is 1 minus cos squared theta. We then have the minus 7 cos theta plus 2, all divided by the 3 plus 2 cos theta. So I'm going to continue working on this and I'm going to expand the numerator. So that's 10 minus 10 cos squared theta minus 7 cos theta plus 2, all divided by 3 plus 2 cos theta. So I have, putting it as a kind of normal quadratic order that we would expect, we have minus 10 cos squared theta minus 7 cos theta plus 12, all divided by 3 plus 2 cos theta. And this is where I sort of feel like we've got a little bit stuck. We want this thing here to end up looking like this thing. And the issue is that we've got a fraction. We've got something in the denominator. And this is where we can try and think, I wonder how I can go from this thing to this thing that we've got on the top. I need this thing to cancel with something here. Now you might have noticed this is what we call a quadratic in disguise or a pseudo-quadratic. And I'm really expecting that when I factorize this bracket on the top, I really expect it to have one of the brackets as a 3 plus 2 cos theta, because then what would happen is it would cancel out and it would hopefully leave me with the thing that I'm looking for, which is 4 minus 5 cos theta. So it does feel a bit sneaky, but we're going to check and see if it actually works. Let's see if the numerator does expand correctly. We have the minus 10 cos squared theta, great. We would have an 8 cos theta and a minus 15. 8 minus 15 is minus 7. And we have the 3 and the 4, which is the 12. So we didn't actually factorize it. We kind of cheated our way to it, but it's a perfectly acceptable way. These cancel out, and so we end up with 4 minus 5 cos theta. Okay, we're now going to have a look at doing part B of the question, which is to actually solve this equation that we've got. So we have our range, and we have this thing. We need to kind of do a bit of spot the difference between this initial thing that we have and this thing. Well, it looks almost the same, right? Apart from anywhere there is a theta, there is a 2x. So I think I can probably rewrite this whole thing that we've got here as this, because if this thing is the same as this, then this thing should be the same as this, but instead of there being a theta, there is a 2x. So the theta has become a 2x, and we can rewrite this whole section that we've got here as a 4 minus 5 cos 2x, and that is equal to the new thing that's on the right-hand side, which is 6 cos squared 2x. Now the range is between minus 180 and 180, so I'm probably going to change that range as well, and I'll say when I change it to a 2x, it will be between minus 360 and 360 degrees that we have. So put this as a quadratic. I think this looks like a pseudo-quadratic. We have our 6 cos squared 2x plus 5 cos 2x minus 4. Now, if you need to, you can say something like, let's y equal cos 2x. So we have y squared is equal to cos squared 2x, which means we have a quadratic as 6y squared plus 5y minus 4. But if you don't need to do this stage, you can just go straight to your calculator and solve this quadratic, because you don't need to show that whole process. You can solve this quadratic with the coefficients of 6, 5 and minus 4. So I'm going to just do that on my calculator now with my quadratic. I'll have 6, 5 and minus 4. And it tells me straight away either y is equal to a half. I'm skipping out that bit and I'm just going to go straight in and say that cos 2x is equal to a half. My other solution is that cos 2x is equal to minus 4 over 3. Now we know that cos can only go between 1 and minus 1. So minus 4 over 3 has got no solutions. This means I just need to solve this one equation here for the range of minus 360 to 360 degrees. So 2x is going to be the inverse cos of a half. I hope you know this one off by heart. It is 60 degrees. For cos, we said in this part here, we will do the other one is 360 minus that. So my other stream of answer, 360 minus 60 is 300. I'll just jot that down. You don't need to show this. I'm just doing it for my video. And then we can plus or minus 360 from these answers so that it goes inside this range. Well, there's no point in adding 360 to either of these answers because they are just going to go beyond that 360. But I will take away 360 from these. So 60 take away 360 is minus 300, and 300 take away 360 is minus 60 degrees. So my last step is to make x the subject, in other words, divide all of these by 2. So I have 30 degrees, minus 150 degrees, 150 degrees, and minus 30 degrees. And I probably would write them in order as minus 150, minus 30, 30, and 150. But if you didn't do that last line of putting them in the right order, obviously there's no error in having done that. You wouldn't be sort of penalised for that at all. So this question kind of pulled in a lot of different things. Really, the only thing you can do with trig to do the identities is just a lot of practice. And you'll spot some of the things I wanted to do here when I had a mixture of sine and cos. I was like, okay, well, I can get rid of this as a sine and make the whole question in terms of cos. The only thing you can do for this is practice. But in theory, This is all of chapter 10 summarized. Now, if you do recognize any of these questions, I have done a couple of videos on like a similar kind of theme. I've done one called Trigonometry Explained. I borrowed some of my earlier work to give you some of these questions that we had here. I've also got one called Differentiation Explained as well. So if you do feel like you've seen these questions before, you're obviously a big enough fan of Bison Maths to have already seen some of my other videos that use these. So thank you for sticking around. Good luck with all of your revision, and I hope to see you in another video soon.